Hi, my name is Dietmar Eggemann. I work as a developer engineer here at ARM's PDSW Processor Division Software Department. Today I want to talk to you about the ARM big.LITTLE architecture running on our first test chip, the TC2. The test chip 2 is a versatile express core tile containing a triple Cortex A7 optimized for energy efficiency and a dual core A15 optimized for high performance. The TC2 does not contain a GPU. Without GPU acceleration, all rendering tasks run on the CPU, which has a big impact on any workload analysis, which we will show later in the demo. Moreover, the TC2 has DVFS, dynamic voltage frequency scaling capabilities provided by a Cortex M3 power controller, as well as per cluster power gating. Now, when it comes to run software on an ARM big.LITTLE system, there are essentially two methods. The first one is what we call migration, where the whole CPU context is switched between pairing big and little CPUs. And the second one is what we call full MP, where the operating system sees, in the case of TC2, all 5 CPUs running in a multiprocessor configuration. Now let's talk about the full MP solution in greater detail. Due to the recently introduced per-task load tracking functionality into the Linux kernel, the MP scheduler is able to know about each individual task load in the system. The MP scheduler creates 2 scheduling domains, one big and one little, and performs standard load balancing only within those domains. There's additional functionality where the MP scheduler checks each thread's workload as it is woken up from the run queue, and based on this information chooses the domain where to schedule the task into. In this video we presented ARM's big.LITTLE architecture running a full MP solution. We showed how a stock Android with enhancement to the Linux scheduler can bring you the benefit of both the highly energy efficient Cortex A7 with a high performance Cortex A15. We believe that this combination can give you the flexibility required for the increasingly demanding workloads found on mobile devices today. Now I want to show you the ARM big.LITTLE full MP solution demo. The system right now is running a stock Android ICS from Lenovo, which you can see here on the right screen. It has a recent Linux kernel with modifications to support the big.LITTLE architecture. The visualization tool is running here on the left screen. It shows for each individual CPU, CPU 0, CPU 1 are the 2 Cortex A15 on the big cluster, and CPU 2, 3, and 4 are the 3 Cortex A7s on the little cluster. The current CPU load, that's the green line, and the CPU frequency, that's the yellow line for the Cortex A15s, and the blue line for the Cortex A7s. It also shows the energy consumption cluster-wide. The yellow area is for the big cluster, and on top of this, the blue area is for the little cluster. Right now, as you can see here, the ICS system is idling. There's almost no load on the little cores, and there's only load right now on CPU 1 on one of the Cortex A15, and that's because of the little screen animation here, the green dots flying to the center of the screen. Like I said before, the TC2 platform does not have a GPU. That's why all software rendering necessary for this presentation is running on the Cortex A15 at the moment, because rendering tasks are high demanding tasks and they end up in the kernel domain of the Cortex A15s of the big cores. Now I will start a music workload. I run audio stream on the ICS system. Immediately the audio tool comes to the foreground, and what you see, this audio tool creates tasks which are running on the little cores. That means the load characteristics of those tasks are such that the MP schedule decides to put them into the scheduling domain of the Cortex A7s. And another thing is important, the load on the A15 stopped, and that's because the audio tool is in foreground, so there is no animation going on right now on the screen. That's why right now both Cortex A15s are idling. Now let me start a second workload, maybe a browser. And what you can see, while the browser was rendering the web page, the energy consumption here on the Cortex A15 cluster, as well as the CPU load goes up on both Cortex A15. That's because software rendering took place and the appropriate task, they ended up in the scheduling domain of the Cortex A15. And when the rendering of the CPU of the web page is done, immediately the load goes down, CPU frequency goes down, energy is going down. So you have a quiet system again. Scrolling of the web page, which I will do right now, has actually a similar or the same effect like creating or opening a web page. You can see the same kind of effects. CPU load goes up on both A15. Immediately, when scrolling is over, goes down. And you see here the little energy spikes for the scrolling of the web page. So I hope that you enjoyed this little demo.